Welcome back to the video lecture series on engineering mechanics. Today in this video, we are going to study the topic wedge friction from the unit friction. In this video, we are going to apply friction concept to solve the problem on wedges. Look at this problem. A block of weight 400 newtons is to be moved by a force P acting on the weightless wedge with an angle of 10 degrees. If the quotient of friction, the angle is 10 degrees. If the quotient of friction on all contact surfaces is 0.2. Find the minimum value of P that required to just move the body towards right. Wedge is a small triangular piece or trapezoidal piece which is used to generally lift the heavy weights or bodies or just to move the bodies, just slightly move the bodies. Usually the wedges are weightless and the bodies will be having heavy weight. By using the wedge, by applying force, we can move the body slightly towards the right side. That is the application or purpose of wedges. Here the wedge angle is given. In the geometry, the wedge edge is making 80 degrees to the horizontal. It is not the wedge angle. The wedge angle is the angle which is made by the wedge surface with vertical. This is 10 degrees. This is 10 degrees. Here, see, if you extend the lines, you will get a right angle triangle. In the right angle triangle, it is 90 degrees. We know that the total angle in a triangle, any triangle is 180. So this is 90 degrees, it is perpendicular. Here it is 80. So the remaining angle is 10 degrees. This is what the angle of wedge. For our calculation, we are going to use the angle of wedge as 10 degrees, not 80 degrees with which it is making with horizontal. Knowing all these values, let us solve the problem to find the minimum value of P required to move the body towards right. If you push the wedge, the body, the block which is having heavy weight will slightly move towards right side. Why we are calculating the minimum weight? Because the reason, if you apply minimum weight, the body will slightly move. After that, any force you can apply to move the body. And if you apply the force which is less than the minimum weight, the body will not move. For that reason, we are calculating the minimum weight or minimum effort required to just move the body right side. Now let us start the solution. The first step is draw the free body diagram for the block first, or you can take the free body diagram of the wedge also, and or you can take the free body diagram of the block. In this problem, I am taking the free body diagram for the block first. Right. The weight of the body is acting vertically downwards, 400 newtons. Now, if the wedge pushes downwards, the block will move towards right side. Okay, the block will move towards right side. Here the normal reaction from the ground is vertically upwards because the block is resting on a horizontal plane. We know that the normal reaction will be always perpendicular to the contact surface. Here the contact surface is horizontal. That's why the normal reaction is upward. Now, if the wedge is pushed downwards, the body will move towards right side. If the body is trying to move or tending to move towards right side, the friction will be always opposite to the direction of motion of the body or impending motion. See, if the body is moving towards right side, the friction will be in opposite direction, that is towards left side at the contact surface. At the contact surface. Here we are considering only block. That's why we are drawing the free body diagram for the body only. We are not showing the wedge here in this free body diagram, but it is existing and it is applying force to move the body towards right. Now coming to the edge which is in contact with the wedge. The edge of the block which is in contact with the wedge is vertical. Therefore, the normal reaction from the wedge is N2, which will act horizontal, because the contact surface is vertical. Therefore, the normal reaction will be always perpendicular to the contact surface. Therefore, it is horizontal. Right. Now, friction. The key point in solving the wedges is the direction of friction at the contact surface between the wedge and the block. Because here the body is not at all moving vertically up or down. The body is not moving vertically up or down. But there is a contact surface. There is a contact surface at which wedge is moving downwards. The wedge is moving downwards, which is not our point of interest, because I am drawing the free body diagram of the block alone. Therefore, actually it is not moving vertically up or down. How to show the direction of friction? The wedge is rubbing against the surface here. The wedge is rubbing against the surface while it is moving downwards. Now, the friction at this contact surface is, even though it is not moving, we can take it as F2 in the downward direction. Why? Because this body is not moving in vertical direction. But we can consider that relative to wedge, actually the wedge is moving downwards. Actually the wedge is moving downwards. Wedge is moving downwards. Relative to that, we can consider this body is moving upwards. Our point of interest is the block here in the free body diagram, which is actually not moving, but the wedge is moving downward. The wedge is moving downward, but our concentration is on the body. If you look at that, the relative motion with respect to wedge of the block, the relative motion of the block with respect to wedge is considered as up. That's why the friction at the contact surface will be considered as in downward direction. This is the key point for solving the problem. Remaining all we can apply equilibrium equations and we can solve them. The only key point is taking the direction of friction when the body is not actually moving. So knowing all these values, let us move forward to find the solution by applying static equilibrium equations. The static equilibrium equations are sum of all horizontal forces is equal to 0. See, look at the free body diagram. Here only two forces are acting in the horizontal direction and they are opposing each other. F1 is towards left and N2 is towards right side. Therefore, N2, F1 minus N2 is equal to 0, or simply F1 is equal to N2. N2 is equal to F1. We know that N2 is equal to mu N1. Why? See, the F1 will be given by mu N1. F1, the friction 1, which is at the contact surface of bottom and the block, is mu N1. See, this is taken from the relation. The quotient of friction is always equal to the limiting friction divided by normal reaction. From this, F1 is equal to mu N1. So this relation is familiar to all of us. So by using that relation, I have substituted the value of F1 in terms of N1. So N2 is equal to mu N1. Now substitute the value of quotient of friction. In this problem, the coefficient of friction for all contact surfaces is given as 0.2. So substitute the values. N2 is equal to 0.2, N1 consider it as equation number 1, which we are going to use further. Now the sum of all vertical components or vertical forces equal to 0. Look at the diagram, there are 3 vertical forces are there. N1 is acting in the upward direction, 400 newtons, the weight always acts vertically downwards, and friction F3 is in vertically downward direction. If you assume the direction of friction F2 wrong, the entire problem will become wrong. We'll get wrong answer. This is very important. Now, N1, which is acting in upward direction, is equal to sum of downward forces. Out of 3 vertical forces, 1 is acting upward and 2 forces are acting in the downward direction. The sum of all vertical components is equal to 0 means sum of all upward forces is equal to sum of all downward forces. Then only the body will be under equilibrium. Now substitute the F2 in terms of N2. N1 is equal to mu N2. The same equation, the same relation I have used, the same relation between friction and normal reaction. Mu is equal to limiting friction divided by normal reaction. So from this, F2 is equal to mu into N2. So this is what the relation between friction and normal reaction, and or otherwise it is a definition of coefficient of friction itself. So N1 is equal to mu into N2 plus 400. N1 is equal to 0.2 N2 plus 400. Again substituting the value of coefficient of friction 0.2, which is given in the problem. N1 is equal to 0.2 into 0.2 N1, because we know that N2 is equal to, that is what our first equation, N2 is equal to 0.2 N1. I am substituting that value back into this equation. N1 is equal to 0.2, that is mu N2, mu is 0.2, N2 itself is equal to 0.2 N1, right? Now N1 is equal to 0.4 N1 plus 400, 0.4 N1 plus 400. N1 minus 0.04 N1, sorry, this is 0.04. N1 is equal to 0.04 N1 plus 400. Correct this equation. This is correct. The second equation is correct. So N1 minus 0.04 N1 is equal to 400. Just I am taking all N1 terms towards left side and numerals towards right side. 0.96 N1. 0.96 N1 is equal to 400. From this relation we can easily calculate the value of N1. N1 is given as 416.66 newtons. Knowing the value of N1, calculate the other values. This is our equation number 1. N2 is equal to 0.2 N1. So from this relation calculate N2 value. N2 is equal to 0.2 into 416.66, 416.66. N2 is given as 83.33 newtons. Knowing the values of normal reaction, now let us move forward to calculate the unknown values of friction at contact surfaces. F1 is equal to mu N1. We know the relation between normal reaction and friction. F1 is equal to mu N1. So the value of friction is 83.33. Even if you consider the free body diagram, N2 and F1 are the forces alone which are acting in horizontal direction. To keep the body under equilibrium by the action of only 2 forces, they must be equal and opposites. See, we got N2 value and F1 value, both are same, 83.33. Now calculate F2 value. F2 is equal to mu into N2, which is equal to 16.67 newtons. Now we get the values, the unknown values of friction and normal reaction for the block. Now knowing the values of friction and normal reaction, now let us move forward to find the value of P, which is required to move the block, just move the block. For that, consider the free body diagram for the wedge. See, the wedge is weightless. If the wedge weight is given, we need to consider wedge weight first. Here in this problem, it is weightless wedge. The force which is trying to push the body downwards is P. That is what we have to find at the end. Now, the normal reaction from the body is N2, which is equal to N2, which we have already calculated in the previous slide. And the friction, see, now the body is rubbing against the block. The wedge is moving downwards and it is rubbing against the wall or surface of the block. Now the wedge is moving downwards. Here in this case, it is easy to consider the direction of friction. Why? Because the body is actually tending to move. When the force is applied downwards, definitely that body will move in the direction downwards only, in the direction of force only, downwards. So here the wedge is tending to move downward. Therefore, at the contact surface, friction will be opposite to the motion of the wedge. So wedge is moving downwards, friction will be in upward direction. But actually in the block case, the body is not moving in the vertical direction, but it is trying to tend to move in the right side, horizontal direction. So it is difficult to assume the direction of friction for the block. That's why it is the key point in the entire problem. Now the friction at the contact surface of wedge and the block is F2, which is acting upward. Already we have calculated the value. Now coming to the other side. The other side, it is moving against the surface. It is moving against the surface or wall. The wedge is moving downwards against this surface, which is making an angle of 80 degrees in the problem. This is not our wedge angle. I will show what is wedge angle. Right. Now the normal reaction always perpendicular to the contact surface. The normal reaction will be always perpendicular to the contact surface. So here N3 is perpendicular to the contact surface and it is making an angle of what? An angle of 10 degrees. It is making an angle of 10 degrees. Look at this. It is making an angle of 10 degrees to the horizontal. See here. This is 90 degrees. This is 90 degrees. This is also 90 degrees. And this is horizontal. This is 80 degrees. And the normal reaction is 90. The normal reaction is making an angle of 90. So this angle is 10 degrees. Let me not complicate this here. Look at this. The normal reaction is perpendicular to the contact surface, therefore it is 90. It is already given in the problem. We know that the total angle in a triangle is 180. So the remaining angle is 30. So it is making an angle of 10 degrees, not 30. It is making an angle of 10 degrees to the horizontal. So that's why it is taken here. Just it is taken here. This is what our wedge angle. This is what our wedge angle. Right. The normal reaction is making 10 degrees to the horizontal. Now what about friction? See, the wedge is moving downwards. So the friction will be opposite to the direction of wedge. That is in the upward direction, F3. If the weight of the wedge is given, we need to consider it in the downward direction. But in this problem, it is an weightless wedge. Now, move forward to apply static equilibrium equations once again. Sigma H equals 0 or sum of all horizontal forces equal to 0. Here there are so many horizontal forces. Look at this N2. N2 is purely horizontal, we can take it directly. Now N3 is making an angle of 10 degrees to the horizontal. So it can be resolved into two components. N3 cos N3 cos 10 is the horizontal component, and N3 sin 10, N3 sin 10 is its vertical component which is acting in the upward direction, and here horizontal component is towards left side. Now N3 cos 10, this N3 sin 10 we will consider in the vertical components. Let us just look at only horizontal components. See, the horizontal component of N3 is N3 cos 10. Now similarly, look at F3. What is the horizontal component of F3? Directly, F3 is making an angle of 80 degrees to the horizontal. So the horizontal component for F3 is F3 cos 80, and vertical component is F3 sin 80. This vertical component we will consider in the vertical components. Now consider only horizontal components. F3 cos 80. There are only 3 horizontal forces. One is N2 purely horizontal, N3 horizontal component, that is N3 cos 10, and F3 horizontal component, that is F3 cos 80, right? So N2 minus F3 cos 10 plus, N3 cos 10 plus F3 cos 80 is equal to 0. See, N2 and F3 both are acting in the same direction towards right side. That's why these two are added, and only N3 cos 10 horizontal component is acting in the opposite direction to that. That's why this is taken in the negative side. Okay. N2, the final equation for the sum of all horizontal components is N2 minus N3 cos 10 plus F3 cos 80 is equal to 0. Now N2 is equal to N3 cos 10 plus F3. I am replacing F3 by mu N3. I am reducing this right hand side to a single unknown value, that is N3. N2 is equal to N3 cos 10 minus mu into N3 cos 80. There is no equal to 0 here. I have taken this N3 terms and F3 terms to the right hand side. So substitute the values now, known values. 83.33, which is N2, is equal to N3 into, substitute the values of cos 10 and cos 80 here in this equation. 83.33 is equal to N3 multiplied by 0.984 minus 0.2 into 0.173. Now further simplify this equation. 83.33 is equal to 0.949 N3. From this equation we can calculate the value of N3. 83.33 divided by 0.949 is equal to N3, which values to 87.81 newtons. 87.81 newtons. This is the value of N3, and we can calculate F3 also. F3 is equal to mu N3. This is our standard relation between friction and normal reaction. Quotient of friction is equal to friction by normal reaction. So by using this relation we can calculate F3, right? So the value of F3 is 17.56 newtons. The friction is 17.56 newtons. Now let us move forward to calculate the unknown value P. So sum of all vertical components equals 0. In the horizontal components, the P is not included. Why? Because it is purely vertical. It will be included in the vertical forces only. Here we will get the equation and we can solve the value of P. So P is equal to F2. F2 is purely vertical, directly it is taken. And we know that the vertical component for N3 is N3 sin 10. N3 sin 10, which is acting in the upward direction. So F2 is upward, N3 sin 10 is also upward, and F3 sin 80 F3 sin 80 is also upward. The P is balanced by the three forces. The P alone is acting in the downward direction, remaining all the three forces are acting in the downward direction. Now substitute the values here. P is equal to F2 16.67, N2 87.81 sin 10 plus F3 17.56 sin 80. The value of P is 49.21. This is the minimum force required. This is the minimum force required to just move the block towards right side. Now, the key points to remember while solving the wedge problems are: the wedge and the body in contact are analyzed using free body diagrams, considering all forces: applied force, normal forces, frictional forces, and the weights. If the weight of the wedge is given, we need to consider the weight of the wedge also in the free body diagram of wedge. Friction forces act opposite to the direction of impending motion or actual motion at which contact surfaces. In case if the body is not moving and it has any rubbing or contacting surface, we need to assume the friction direction by using the relative motion against the other body. Relative motion to the other body. The equilibrium equations can be used to find the unknown values of friction, normal reaction, and any other reactive forces. If the weight of wedge is given, it must be included in the free body diagram and in equilibrium equations. Thank you.